Alright, so we're going to go ahead and talk about SPI in this tutorial. So what exactly is SPI? It stands for Serial Peripheral Interface, and it is a digital communication protocol used to transfer data between devices. So let's go ahead and get started with this little image here that describes exactly how SPI works. So we have this thing called master and this thing called slave. So the idea is master is the master device, or say a microcontroller, that helps to operate each of these little slave devices. So the slave devices are peripheral devices. These could be like sensors or something like that. And what it pretty much means is this microcontroller gets to define exactly what it wants to send out and what it wants to read in from these slaves. So with that, there's also a variety of different pins that the master has that are kind of the same for the slaves. So the first one is S clock. So this is serial clock. And what this pretty much does is it helps to output a clock signal. And the advantage of the clock signal, if you watch the I2C tutorial, it pretty much helps to make it so that when the data gets transferred across, it gets interpreted at the same rate as it is transferred, just to help ensure that no bits get lost in the transfer, and just to help to double check that nothing gets misinterpreted. Okay, so the next one is MOSI, and this is master out slave in. And so that pretty much means the master is going to transmit stuff out, and the slaves are going to read the stuff in. So this is effectively the transmit pin for the master. So the transmit data that use the MOSI pin. The other one is MISO, and if you might have guessed it, it's master in, slave out. So master in, slave out pretty much is the receive pin for the master. So this is the pin that it receives data from the slaves. Okay, and there are these things called SS1, SS2, and SS3. So these are slave select pins. And the idea behind these slave select pins is the idea behind the scalability of how SPI works. So as you can see, all these slaves are connected via the serial clock, the MOSI line, and the MISO line. So the way to make it so that the master distinguishes exactly which one it wants to communicate with, it determines that by the slave select. So when the slave select is pulled low, so say SS1 is pulled low, that means the master wants to communicate with this particular slave, so the first slave. If SS2 is pulled low, then it wants to communicate with the second slave, and SS3 is pulled low, then it wants to communicate with the third slave. So there's a little small perk here. You have to make sure that you don't have two slave select pins pulled low at the same time, because that's going to mean that you're going to be reading stuff with two slaves simultaneously. And if they're connected to the same, receive pin, that means it's going to corrupt the data, and it's not going to make any sort of sense whatsoever. So by default, all these slave select pins must be pulled high, unless if you want to actually communicate with one of them. And if you want to communicate with them, you just pull this digital pin low. So that's how it works. And the idea is that as you add more and more SPI slaves, you're going to be needing an additional slave select pin for each slave. All right, for the sake of demonstrating SPI, what we're going to do is for the master device, we're going to use the KL25Z. And it's going to interface with a sensor called the LSM D9S0. And what this pretty much is it's effectively a super sensor. So it's one chip that has a gyroscope, accelerometer, and a magnetometer on it. And this is a $5 device, and so it's $5 for 3 sensors, but actually not that bad. So each of these, if you were to actually buy this individually, costs you between $3 to $10, depending on the accuracy. So yeah, it's actually pretty cost effective. Now, there's a side consequence of this, though, is the fact that ST Microelectronics, which was the company that made this, what they pretty much did was they got their gyroscope and they got their accelerometer and magnetometer device, and they just smashed them together. So instead of actually making a really integrated circuit where it would actually access as only one slave device, they pretty much left it alone and just went ahead and said, you know what, we're going to make it so that there's one SPI slave device, which is the gyroscope, and there's going to be the second SPI slave device, which is the accelerometer and the magnetometer. So with this, this one chip actually acts as 2 devices. And so with that in mind, we're going to have 2 slave select pins. Now, another thing to keep in mind is that the LSM-D9S0 does in fact have an I2C interface. So if you wanted to, you could also use I2C for this. But we're going to use SPI for one very good reason. So If you've watched the I2C tutorial, I previously said that 400 kilohertz is roughly, the the maximum speed that you can actually have to transfer data across. Now, for SPI, that's different. The fastest clock speed you can have is half the speed of whatever your master's clock is. So in the case of the KLA25Z, this thing runs at 48 megahertz. That therefore means that for the serial clock, we can actually jam this up to 24 megahertz. However, there's one small perk about this, though, is that the LSM-D9S0 has a maximum clock rate of 10 megahertz, so we can only jam it up to 10 megahertz. However, this is actually pretty beneficial for us because with the gyroscope and accelerometer and magnetometer, and we're having this all running at the same time, expect to have a lot of data coming in back and forth. So the faster clock rate helps it so that we can actually transfer stuff a lot faster than we would if we used I2C. Now, with this in mind, there's quite a lot of devices that we need to work on and actually accessing and using. So for the first part, we're just going to access the gyroscope data, and then after that, we'll go ahead and add on the accelerometer and the magnetometer on top of that.